All right, welcome back. This is going to be the 7th video here in the S1 equation series. In this video, we're going to discuss how we determine S1, or how we determine our go, no-go decision point, and how we calculate reference zero. So far, we've discussed that S1 cannot be higher than the lowest of refusal speed, maximum braking speed, or rotation speed, as well as S1 cannot be lower than the highest of critical engine failure speed or ground minimum control speed. Now that we understand the equation, it is time to discuss the most important aspect, how we apply the equation to our day-to-day operations. So how do we choose when to be committed to the takeoff? In our operations, we are usually very stop-oriented, meaning we usually utilize the decision to abort as long as possible. When choosing S1, we usually set S1 to be one of the variables on the right side of the equation. Now, why do we do that? Well, the reason we don't choose S1 too early, or we don't choose S1 to be critical engine failure speed or ground minimum control speed, is because if we chose those speeds, we would limit our chance to make a decision to abort. We usually encounter these two speeds at lower indicated airspeeds. So we choose S1 normally to be one of the right side of the equation variables, be it refusal speed, maximum braking speed, or rotation speed. What this does is it increases our time to make a decision to abort if a malfunction or an emergency occurs. Now, more often than not, we are actually going to encounter our rotation speed before we ever encounter refusal speed or maximum braking speed. This isn't always, but most of the time, we set S1, or our decision to commit to the takeoff, as rotation speed. Now, there will be times when S1 does not equal rotate, represented as this, but S1 may equal refusal speed or maximum braking speed. We'll get into that in a little bit. Next, we're going to discuss reference zero. Reference zero is the point in space at the end of the takeoff flare distance at which the aircraft reaches 50 feet above the runway elevation. Reference zero will occur no later than the departure end of the runway. Our rules, stated in the 2T1 Vol 3, say that for takeoffs, our minimum runway length has to be at least 6,000 feet or distance to reference zero, whichever is greater. So how do we determine that? Well, first, how do we know if our runway is at least 6,000 feet? Well, first, in mission planning, I want to make sure within the IFR SUP, or the IFR supplement, or the Airport Facility Directory, or AFD, I'm going to look at the takeoff runway available, or TORA. As long as the TORA is greater than or equal to 6,000 feet, I've met the first requirement as stated in our rules for our minimum runway length. The next portion it talks about is our distance to reference zero. So how do I calculate my distance to reference zero? Well, there's two ways, and that has to do with S1 and rotation speed. So when S1 equals rotation speed, reference zero is equal to our takeoff ground run plus takeoff flare distance. And what that looks like here is there's our rotation speed and there's our T1. The amount of distance it takes for us to accelerate on two good engines normally and reach rotation speed is called our takeoff ground run. When we hit rotation speed and rotate to take the aircraft airborne, we reach reference zero. So from rotation speed to the point in space where we reach 50 feet above the runway, that distance is called takeoff flare distance. And when S1 equals rotation speed, reference zero is calculated by combining takeoff ground run plus takeoff flare distance. And the second way we calculate reference zero is when S1 does not equal rotation speed. So S1 may, in fact, equal either refusal speed or maximum braking speed. If that's the case, we're going to calculate reference zero by combining our critical field length plus takeoff flare distance. So what that looks like here, there's our T1. And we remember what critical field length was, right? That means we've hit critical engine failure speed, lost an engine, and decided to continue. So there's our engine failure at critical engine failure speed, and we decide to continue. The distance it'll take for us to accelerate to rotation speed here is known as critical field length. And when we rotate to take the aircraft airborne, when we reach 50 feet above the runway, that distance, that lateral distance, is called takeoff flare distance. Notice here that when S1 equals rotate and when S1 does not equal rotation speed, we still use takeoff flare distance. That doesn't change because takeoff flare distance assumes one engine inoperative once we've hit our rotation speed and rotate to take the aircraft airborne. So to summarize, when we calculate our distance to reference 0, we have to consider whether or not S1 is equal to rotate. And when we determine the minimum runway length required, we're going to look at either is the runway 6,000 feet or is our reference 0 greater. And whichever we determine as greater is now going to be the minimum runway required for our takeoff. And in the following videos, we're going to figure out why, when S1 does not equal rotation speed, why do we use critical field length versus takeoff ground run.